Okay,
Hello,
perfect.
Armando.
Hi.
Hello, Jorge. Now we are also
Hi.
live on YouTube. I think that today I
Okay.
did things all right. I can see yeah. Okay, because I tend to launch the YouTube too late. Now this is already working.
Okay.
So let's wait a little bit more. We are still 3 minutes. Some people are logging in, 16 already.
Okay.
Okay, hello to everybody.
I'm trying to share my screen and
Perfect.
test if everything is all right.
Uh-huh.
Okay, I cannot. So
You can share your screen because I didn't give you permission. Okay, you're too fast. Now you have my permission.
Okay. Okay.
Okay, and now you should be able to share. Great.
Okay.
Constant motion, identifying ESQPTs.
Okay, and I turning on my cam again because I don't know why when I share my screen the cam turns out. So I think everything is all right, no?
Yes, I can see you and I can see your screen perfectly. Okay. Your PDF, or yes, it's a PDF. Constante.pdf.
Yes. When I start, I put in the whole screen. So then tell me if everything continues all right, because when I'm now presenting my slides, I cannot see you. I cannot see the Zoom screen because I'm seeing the PDF file.
Yeah, that's quite inconvenient. Yeah, it's not very efficient, but
Okay,
but that happens with Google Teams. That happened to me, not with Zoom. With Zoom, I used to work better with that with the Teams, but Google Meet was not Microsoft Teams. So we're already 20, but still okay. One more minute, a couple of minutes. Jose Enrique is already here too. Okay.
Hi.
Oh.
Armando, I'm not sure if you have very good connection because sometimes it kind of cuts your voice for me. I don't know.
Do you listen to me now? Because
yes.
I'm with Wi-Fi, so I don't know if it's properly working or not.
Yeah.
Or maybe you can disconnect your camera.
Okay, I switch off the camera. Maybe
also, there are many open microphones now. Once we close the microphones and the seminar starts, probably this will improve. Okay.
Okay. So I'm turning on my cam again, and if there are some problems during my talk, you tell me, and I switch off the camera.
Okay.
Okay.
Okay. Perfect. Perfect. So it's already 4:01. So let's start, and I think that everything is all set. We have YouTube recording, and also the seminar is being recorded in Zoom. So this is a new seminar on the ESQPT 2021 seminar series. And we are very happy today to host in this seminar series Armando Relaño, who I met a long time ago. He did his thesis in the Universidad Complutense de Madrid on quantum chaos. And since then, he has been working on quantum chaos. And I think that he is now one of these reference figures in the field of quantum chaos, somebody who has published many very interesting papers and with a high impact. He spent some time with Oriol Boigas in the group where really quantum chaos started, was born, this concept of translating from the classical realm, this very fashionable and hot topic of chaos, to the quantum realm, which is something that is not at all direct, and it's still posing many open questions. Then he spent as a postdoc some time in the Consejo Superior de Investigaciones Científicas in the Instituto de Estructura de la Materia, and then he went back to the university, where now he holds a position there. He has supervised several PhDs, and as I said, it's a very well recognized figure on the quantum chaos field. Though nowadays he has other interests. He is also working on quantum statistical mechanics, and also the problem of measurement in quantum mechanics, and some quantum paradoxes. So he's a brilliant speaker. And today he will speak to us about how to define constants of motion, identifying the different phases in ESQPTs, something that, as Pavel mentioned, it's an open problem nowadays in ESQPTs, how to identify phases. So, Armando, it's all yours.
Oh. Thank you, Curro, for this nice presentation, and also thank you to you and Jose Enrique for organizing this seminar series, usual trips to Huelva. So I'm very happy to have this opportunity to see you online and to discuss a bit about physics and about excited state quantum phase transition. So as you have said, the topic of my talk is trying to convince you that we can define different excited state quantum phase relying on a constant of motion that splits the spectrum into different phases with very different thermodynamic properties. This is an ongoing work with my PhD student Angel Lopez Corps, and so I'm very glad that you interrupt me whenever you want to discuss all the things you have in mind related to this topic. So as I will start with a brief definition of an excited state quantum phase transition. So as Pavel Ternar told us in the first talk of this series, we can understand an excited state quantum phase transition in the following way. Let's suppose that we have a Hamiltonian which depends on an external parameter, and we can define this excited state quantum phase transition as a non-analytic behavior in the level density and or the level flow in the plane composed by the energy and this parameter. So this is normally understood as a generalization of a standard quantum phase transition which takes place in the ground state. So normally we understand that this excited state quantum phase transition is more or less the same in the excited state of the system. But this definition, from my point of view, is correct regarding the singularity of the level density, but it does not cover all the features of standard quantum phase transitions. To see what I'm saying, let's consider a very typical example, which is the Rabi and Dicke models. This model has been used in previous talk on this series, for example, by Sergio Lerma or by Ricardo Puebla. So this model has very interesting features. One of them is that it has two different thermodynamic limits. One of them is the normal one, in which the set of atoms which compose the system goes to infinity. We have an infinite number of particles, but we have another different thermodynamic limit consisting in an infinite ratio between the frequencies for the atoms, this term multiplying the third component of the angular momentum, and the frequency related to the bosonic field. This is very interesting, and we see in a while some examples of this Hamiltonian. Now, from my point of view, it's interesting to see what happens in the quantum phase transition happening in the ground state. We know that there exists a critical coupling separating two different phases. At this value of the coupling, we see a non-analytic behavior, which is the singular point, the critical point, but also we have that there are two different phases at both sides of this critical value, the coupling constant. So this is important for the following reason. Let's imagine that I am working with a group of students and I want to know if they understand correctly the physics of this model. So I asked them to prepare the Rabi and Dicke models in either the normal phase or the superradiant phase, as they want. So I let them working, and when they are finished, I test if they have done the work correctly. So this is very easy to me because I just have to measure a magnitude. In particular, I can measure the number of photons, and I can test if they have prepared the state correctly. If I measure that the number of photons is equal to 0, I get that I am in the normal phase. If I measure that the number of photons is larger than 0, this means that I am in the superradiant phase. So if we think that the properties of this quantum phase transition are translated into excited state when we are dealing with excited state quantum phase transition, one would expect something similar happening in the spectrum. This here I plot a Perez lattice that is the expected value of the photons on different eigenstates of the system in terms of the energy of the system. So I'm here in the coupling constant corresponding to the superradiant phase. This means that the ground state here is in the superradiant phase. So if we expect that the properties of the quantum phase transition are translated into excited states, this would mean that crossing this critical line entails something like passing from a large number of photons to very small or even 0 photons. You can see in this figure that this not happens. This is completely different when what we see if we diagonalize the system and calculate the number of photons in the different eigenstates. Maybe you can think that there is a difference in the low energy region. You can see an order pattern, but this is because in this region, the system is more or less integrable, and in this region, the system is chaotic. And this is not related to this excited state quantum phase transition. This means that I cannot do a similar experiment for studying the excited state quantum phase transition. I mean, I need another definition for different phases. And now I'm going to summarize some ideas which can allow us to define different phases regarding the excited state quantum phase transition. The first one was discussed by Pavel during the first talk on this series. It's an idea showing that when we change the energy of the system, the response or the susceptibility of the system is different in different phases. In this, I have borrowed this figure from this nice review of Pavel, and we see here 3 different critical lines and 3 different behavior for the slope of a third-time observable in terms of the energy. This means that if I prepare an equilibrium state in one of these phases and I give work to the systems, I observe a different response depending on the phase in which I am. This is nice. This is nice. Of course, this is a clear difference, but it's more complicated than the idea I have discussed before regarding the quantum phase transition, because this is not an order parameter which is 0 at one side of the transition and which is different from 0 at the other side of the transition. So if we want to propose something like an order parameter, we have to rely on different ideas. With Ricardo Puebla and I tried to do this a few years ago, and we work with 2 different systems with having excited state quantum phase transition. We work with the Lipkin-Meskov-Glieb model here on the left, and we work with the Dicke model on the right. What we observe is that if we measure symmetry breaking observable like the first component of the angular momentum, we get a value different from 0 at one side of the transition and a value equal to 0 at the other side of the transition. And this is a very good result because it allows us to propose that this symmetry breaking observable acts like an order parameter. But there is a but. The main problem is that this is not working always. 2 years later, we did a numerical experiment showing that we can be in the region below the critical energy, having a 0 value for this first component of the angular momentum. What we did is to start, let's say here in a slow value for the energy, having a large value for this observable, and we started to change the coupling constant of the system very slowly, not to dissipate energy, up to we cross the critical line and we get to the phase in which this order parameter is equal to 0. So this is what we did in this blue curve when the arrow pointing to the left. And then we came back to our original state. As we did it slowly, we could cross again the critical line and came back to the original phase. And what we observed is that our order parameter didn't come back to the original value, but remain around 0. This means that we can be in the same phase having either this order parameter equal to 1 or this same order parameter equal to 0. And this means that this is not perfect in the sense that we can be we can have different values being in the same phase. So this means that this requires deeper explanations. So we come back to this point further on. I'm now exploring other ideas. Some of them are related to the classical trajectories of the classical analog of the system. In this work here of the group of Manuel Gessner, the authors studied an excited state transition happening at an spin-OR condensate. This is a very nice system which can be described by a single degree of freedom classical Hamiltonian, and what they observe is that they can characterize different phases by means of topological properties of classical orbits. They fix their attention in a singular point of the phase space, this point here with this vertical arrow, and they observe that below the critical energy, the classical trajectories here in yellow do not surround this singular point. And above the critical energy, these trajectories here in green do surround this singular point. So they were able to define a winding number characterizing this change of phase. This winding number is 0 below the critical energy and is +1 or -1 above the critical energy. So we have a property of the classical orbits which allows us to distinguish two different phases. So this is classical, and probably it's interesting to have a pure quantum property or pure quantum signature of this change of phase. So I'm showing you here a nice work of Wong and Curro. They work with the Lipkin-Meskov-Glieb model, if I'm not wrong, and they found something similar than the previous work, but with a Husimi function, which can be understood like a quantum version of the classical phase space. What they observe can be summarized in this figure here. In the upper row, they show the dynamics when the system is below the critical energy. So this point here represents the initial condition, and they let the wave function evolve. And what they observe is that the wave function remain, let's say, trapped at small part of the quantum phase space. In particular, if we think in the previous language, it would be like this central point would be this singular point at the wave function do not surround this point. The central row corresponds to the critical energy, and now we see that the wave function crosses itself and passes through this singular point. This low row corresponds to an energy value above the critical energy, and now we see that the wave function surrounds this singular point. So the idea that the properties of trajectories or properties of the phase space give us a clue about the phases in which we are, it's now even deeper with a deeper support, because we can see here that we can study it in terms of pure quantum functions. So with this idea in mind, I'm going to rely again in classical mechanics to try to distinguish two different phases at both sides of an excited state quantum phase transition. We also know that relying on classical mechanics is very useful because we can detect the critical points by looking for points which are singular in the Hamiltonian flow. In particular, fixed points for the classical Hamiltonian flow corresponds with the critical values corresponding to an excited state quantum phase transition. So in the examples I have discussed before, we have two different thermodynamical limits in which we can test the results. And in particular, relying on this condition, we can predict the energies at which the excited states quantum phase transition take place. So what I'm going to do now is to show this classical dynamics for the Rabi model to understand the properties of these classical orbits. I show here the constant energy curves for the Rabi model in this thermodynamic limit for different energies. Here in this plot, I am below the critical energy. What we can see here is these constant energy curves are split in two parts, and both parts remain trapped at one side of the classical phase space. Let's imagine, for example, that I start my evolution in initial condition here. What I obtain is that this trajectory remains in this region and does not cross to the other one. So, and the same happens here. I start with an initial condition in this part of the phase space, and I remain in this part of the phase space. So if I increase the energy, I see the same. Now this curve is larger, but it has the same property of being trapped either on the left or on the right part of the phase space. Here I am still below the critical energy, and here I am exactly at the critical energy, which happens at this particular value. This figure is a bit weird because we have that this curve of constant energy crosses itself, so we have here a singular point. What happens in terms of the trajectories? Well, if I start, for example, here at this point as an initial condition, I start to move following this curve, but I need an infinite amount of time to reach this point. So the trajectory never reaches this point, and of course the unicity of the solution is not broken. This means that exactly at the critical energy, the trajectories are still trapped at one side of the classical phase space, because the trajectory remains on the left or remains on the right, depending on the initial condition. Next, if I increase the energy and I cross the critical line, what I get is a trajectory which passes through both parts of the phase space. I start here and I follow the trajectory, I cross this separation line, and I continue at the other side of the phase space. So what I see is that the properties of the classical trajectories are very different at both sides of the excited state quantum phase transition. Below the energy, we have that the trajectories are trapped either with a position less than 0 or position large than 0, and above the critical energy, the trajectories change from negative coordinates to positive coordinates, and so on. So this is for classical mechanics. We can wonder what happens in quantum mechanics. So I'm borrowing again this figure from Curro and Wong, and what we can see here is that the quantum evolution is somehow different. Curro and Wong did a work in which they started from the same initial state, and we can see that the trajectory depends on the energy. If we are below the critical energy, the trajectory remains, the wave function remains trapped, but if we are above the critical energy, the wave function starts to cover all the possible points in the phase space, and the dynamics is totally different from the classical one. I mean, in the classical world, we cannot have an initial condition here which spreads over the whole phase space after some times. And also, we can find superposition of both parts of the phase space. This is what we are observing here. We have not a wave function trapped either on the left or on the right, but we see a wave function which is in a superposition of both possibilities. So it's not so clear how to translate the classical results into the quantum world. And this is what I am trying to do here. So I'm trying to translate the classical features, the classical dynamical features, into quantum thermodynamics. So to do so, I'm going to be a bit more, let's say, following a bit more mathematical language. So let's consider that we have a quantum system which has a classical analog we can write as a Hamiltonian function of position and momenta. We can have any number of degrees of freedom. This formally is not restricted to 1 or 2 or 3 degrees of freedom. It has to work with any number. Normally, this kind of system has have a small number of degrees of freedom, but in principle, we can have any number of them. So we have this classical Hamiltonian, and we need a dynamical function f, which is a function of the same coordinates and momentum, having the following properties. If we are below the critical energy, this dynamical function is always trapped on the left, that is, it's always smaller than 0 or larger than 0. That means that the trajectories are trapped in one part of the phase space corresponding to negative value of this function, or trapped in the other part of the phase space corresponding to positive values of this function. The example of the Rabi model, which I have shown before, fulfills this requirement, and there are a large number of systems fulfilling this requirement, in particular Lipkin, Dicke, etc. And we need also that above the critical energy, this separation is not holding. I mean, any trajectory passes through positive and negative values of this dynamical function. This is the idea. Of course, depending on the system, we can have different dynamical functions. So we have the work to find the correct function for the system we are working with. So having this classical dynamical function, we are going to translate it into the quantum language. First, we define the quantum operator for this dynamical function, which is quite easy because we just quantize the coordinates and the momentum. And then we are going to define a special operator, which is the sign of this dynamical function, of this quantum version of the dynamical function. In the classical world, maybe this is not making a lot of sense because taking the sign of a dynamical function is something weird. I mean, we get in this way a non-analytical function which jumps from -1 to +1, and probably this is not a good idea. But we are in the quantum world, and we have a precise definition of this sign. I gave here 2 different ways to calculate it. For example, we can diagonalize F, then we can get a diagonal matrix with the eigenvalues, we can take the sign of each one of the eigenvalues, so obtaining a diagonal matrix with +1 or -1, and then come back to the original basis. This is a practical way to calculate in numerics, but we have also, let's say, more elegant way of defining this, this operator in terms of this integrable here, which involves the operator f and the inverse of a theta operator, which is a function of f squared. So the idea now is that we have an operator which is well defined and has two different eigenvalues, plus and -1. So this operator is something similar to a parity or a time reversal, which are discrete operators having just two different eigenvalues. So we have this operator, and what can we do with it? So let's consider that we write the Hamiltonian as a linear combination on the projectors of the different eigenspace in this way. So what we propose as a conjecture is that this operator C commute with all the projectors corresponding to energy levels below the critical energy, and that this operator does not commute with all the projectors corresponding to energy levels above the critical energy. We formulate here in terms of a conjecture. I wish we can prove it mathematically, but I think that it is almost impossible because it would require having the analytical solution for the projector, for example, for the Dicke model, and this is, I think, totally impossible. So we formulate it in terms of a conjecture, and in the following slide, we will show some numerics trying to convince you that this is true. So before to do that, as a corollary, we can conclude that if this is true, if we have an initial condition with an energy below the critical energy and being narrow in energy, what we are going to obtain is this C is going to be a constant of motion. And this is not expecting to happen if we are above the critical energy. This means that this new constant of motion acts like a discrete symmetry below the critical energy, so it is like a parity or a time reversal symmetry. So, okay, which consequences these facts implies? So, in this nice paper, these authors show that thermodynamics is completely different when we have several or multiple conserved quantities in a quantum system. In particular, they show that irreversibility is not linked to energy dissipation under these circumstances, but it is linked to dissipation in all the conserved quantities. I mean, we can have no energy dissipation if we have dissipation in the conserved quantities, and in this case, the process is irreversible. I am also involved in this kind of results. In this paper, we showed that using fluctuation relations that describe non-equilibrium quantum processes, we can detect the existence of conserved quantities. I mean, this implies that if this operator C is a constant of motion in the phase below the critical energy, it has to imply consequences also in non-equilibrium processes. So with this idea in mind, we are going to apply these results to the Rabi and Dicke models. So I came back to the trajectories. We can see that in this case, this dynamical function which splits the phase space in two different parts is quite easy because it's just the coordinate q. So we propose that the quantum version of this coordinate, this combination of the creator and annihilation operator for the photons, is a constant of motion below the critical energy. So I am going now to test these results by numerics. What I'm going to do? I'm going to start from an initial condition, which is a superposition of different eigenstates of both the Rabi and the Dicke model. I have chosen a superposition of 10 different eigenstates with the same weights. So, and then I am following the evolution of this initial state. I'm calculating the expected value of this operator C, and I am also calculating the dispersion of this magnitude in time. If this sigma 2 squared is equal to 0, this means that this evolution is constant, so this operator C is a constant of motion. If this dispersion is different from 0, is larger from 0, this means that the dynamics does not conserve this quantity. And then I am going to show different initial states corresponding to different energy. This is the idea. So I show you results here for the Rabi model. So I'm using this ratio of frequencies, which can be interpreted as having 300 particles. Ricardo Puebla explained us the other day the meaning of this thermodynamic limit. So maybe an easy way to understand it is considering like we have 300 particles and we are in the thermodynamic limit, we have an infinite number of particles. As we can see here, I plot here as a vertical line the critical energy. We can see that below the critical energy, this dispersion is equal to 0. So that means that this observable C is a constant of motion, and we observe an abrupt jump exactly at the critical energy, and above the critical energy, we obtain a dispersion larger than 0, meaning that this C is not a constant of motion anymore. So with the Rabi model, we obtain numerics that are fully compatible with our conjecture. What happens in the Dicke model? In the Dicke model, we obtain similar results, not so beauty, because we need more computational resource to diagonalize the Dicke model, and I can show you results for 40 atoms instead of 300 particles as I used before. Anyway, we observe that this dispersion is 0, clearly below the critical energy. Then we observe a jump, and then we observe a small decrease, but at the end, we remain in a positive value for this dispersion, meaning that above the critical energy, this operator C is not a constant of motion. To get more precise results, we have also done finite size scale analysis. I show you the results here for the Rabi model, how this dispersion evolves when we change the energy and we change the, let's say, system size. The blue case, the upper line, corresponds to an energy value above the critical energy, which is in -1, and the other two corresponds to results below the critical energy. So let's take a look on the scale on the y-axis, and let's have in mind that it's a logarithmic scale. I mean, we obtain values up to 10 up to -32, which is the precision we have in quadruple precision. We have done this calculation in quadruple precision result. So what we observe is above the critical energy, the evolution of this operator C is not constant for any of the available size system size, and below the critical energy, the dispersion is decreased up to it reaches the precision of the computer. So with the Dicke model, we observe a similar results, but they are not so spectacular because we are with a small number of particles. So I have written here 40. Of course, this is not correct. The real number of atoms changes with different sizes. So we start below 10 atoms and we reach up to 50 atoms. What we observe is that the constant behavior for this operator C is better as we increase the system size if we are below the critical energy, And we also observe that this C is not constant if we are above the critical energy. So after these results, we can be confident about this conjecture, and we are going to try to understand a bit more about its mathematical and physical properties. So we are going now to explore these properties. To do so, we are going to consider that both the Dicke and the Rabi models have a discrete symmetry which holds in the whole spectrum. I mean, we have an operator, the parity, which commute the Hamiltonian, and we can define the parity in this way. It's very easy to interpret this because this parity measures the parity of a number composed by the number of photons plus the number of excited atoms. So if we increase by 1 the number of photons, or we increase by 1 the number of atoms which are in the excited state, we change the parity. This means that we can diagonalize the Hamiltonian in an eigenbasis, which is also an eigenbasis for the parity operator, and we can label the energy levels and the eigenstates with two quantum numbers, one corresponding to the parity plus 1 or minus 1, and the other one corresponding to an order in the energy scale. So if our previous conjecture is true, this means that below the critical energy, any statistical ensemble or any thermodynamical description must depend on the Hamiltonian, the parity, and this new operator C, and above the critical energy, these properties, the statistical ensemble, only depends on the Hamiltonian and the parity. So it's very interesting to see or to study how this constant of motion lives with the parity and how we can relate these two guys. So this is what we are going to do now. So to do so, let's consider this definition of the constant of motion and this definition for this F dynamical function for the Dicke or the Rabi models. So as I have said before, the parity is more or less the parity of the number of photons plus the number of excited atoms. This means that if we apply this operator F to a state having a well-defined parity, we change the parity. We change from positive to negative parity or vice versa. So if this F changes the parity, this means that this F to the square keeps the parity because it's operated 2 times the change of parity. And this also means that this combination, F to the square plus X squared by the identity for any value of X, commutes with the parity. The same happens for the inverse of this operator, because as F squared plus X to the square by the identity works on an eigenspace of parity, the corresponding inverse operator also works in an eigenspace of parity. And finally, if we perform this product here with keeping with an observation commuting with parity and an observation changing parity, what we get is the argument of the integrable change parity always, and therefore the operator C change parity in any case. That means that if I apply this operator C to an state with a positive parity, I have to get an state with a negative parity. And what does this imply? So let's consider that both the parity and this operator commute with the Hamiltonian below the critical energy. That means that if I act with the parity on an energy eigenspace, I'm going to remain in the same eigenspace, whatever the energy is. And if I am below the critical energy, if I act with this operator C in an eigenspace of the energy, I remain in the same eigenspace of the energy. But I also know that this operator changes the parity. And the only possible solution to that is that each one of these eigenspace has at least dimension equal to 2, because I need two different eigenspace, two different states in order that this operator C can change from one to the other, remaining in the same eigenspace. So that means that below the critical energy, the spectrum must be pairwise degenerate. This is a fact that we knew before from the Dicke and the Rabi models, but now we can interpret it as a consequence of having this constant of motion. I mean, if I define this phase as the phase having this constant of motion, I get that it has the energy levels have to be pairwise degenerate as a consequence of having this constant of motion. So I consider that it is an interesting result since it explains a well-known property of this excited state quantum phase transition. More things. Then we can also get a result for how this operator acts on this this basis, which is also an eigenbasis for the parity. As we have said before, this operator C changes the parity. That means that these two equations must hold because we change always the parity. And also, we know that this operator C has two different eigenvalues, +1 and -1, and we know that the corresponding eigenstate has to be linear combinations of the two eigenstates of the parity if we are below the critical energy. We also know that this operator is real, so we get just two different solutions for this 4 equation. One of them is that this constant alpha and beta are equal to 1, and the other one is that this constant alpha and beta are equal to -1. So it is possible to find these two solutions. Which one is the correct one? Well, we have here an ambiguity. Let's see in the following way. Let's imagine that I have diagonalized the Dicke model using a numerical routine. And this numerical routine has obtained an eigenvector with positive parity and an eigenvector with positive parity, both with the same energy. So let's imagine now that I just change the sign of the second one, the eigenvector with negative parity. If I do this, this eigenvector is still an eigenvector of the Hamiltonian, and it is still an eigenvector of the parity with eigenvalue equal to -1. This means that there is an arbitrary sign among these two eigenstates of the same energy subspace. So, and this is the reason I have two different solutions which depend of this arbitrary sign. So depending on the details on the numerical calculation, I can get this solution or this other one solution, and I can fix one of these two branches just considering with a bit of care the relative signs between these two different eigenstates. So we can now perform a second numerical test to see if these properties are holding in the Dicke and the Rabi model. So what I'm going to do is I'm going to get a particular eigenstate with positive parity, and I'm going to look for another eigenstate with negative parity, which is close in energy to the former one. So imagine that I get an energy equal to -2. So I look for another eigenlevel with negative parity closer to -2, and I study the difference between these two energies and this operator, which is, remember that this sandwich here is equal to +1 or -1 if we are below the critical energy. So 1 minus the absolute value of this guy here has to be equal to 0 if we are below the critical energy, and has to be larger than 0 if we are above the critical energy. So I can test if these two things are fulfilled below the critical energy. So I do this in the Rabi model, again using the same values for the energy than before, and relying again on quadruple precision calculation. What we observe is the same that before. Above the critical energy, this sandwich is not equal to +1 or -1, meaning that the operator C does not commute with the corresponding projector. And below the critical energy, this sandwich is equal to +1 or -1, showing that this operator commutes with the corresponding projector. And let's see that we reach again the precision of the quadruple precision calculation quite early in terms of the system size. The same result is obtained for the Dicke model. So in this case, again, I'm not reaching the precision of the calculation because I'm dealing with a smaller system. If I could diagonalize the Dicke model for 300 atoms, I would obtain something similar that I have obtained with the Rabi model. So this is the result for this sandwich for the C operator. We can obtain a similar result for the degeneracy of the energy of the pair of energy levels. Again, below the critical energy, we observe that this degeneracy tends to 0 as we reach the thermodynamic limit, again with the same values in the Rabi model, and we observe more or less the same behavior for the Dicke model. Again, we observe that this distance between energy level decreases with the system size above the critical energy and remain more or less constant above the critical energy. This means that we have yet two different numerical tests, one dynamical regarding the time evolution of a certain initial condition, and another static regarding the properties of the energy levels and the eigenstates of the Hamiltonian. So we have covered a quite broad numerical experiment to show that our conjecture is true. So having these results in mind, I am going to make a final numerical test regarding the thermalization or the equilibrium states in these Rabi and Dicke models. So what we are working with is we start from an initial condition, we let the system evolve unitarily, I mean without any link with an external bad heat or something like that, and we follow this time evolution. We know that in this way we cannot get an equilibrium state because of the unitary of the Schrödinger equation. But we also know that the time evolution is close to an effective equilibrium state. So let's consider an initial state, which is a combination of positive parity eigenstates and negative parity eigenstate. We know that this time evolved state we can write in terms of a density matrix, which has two different kind of terms. One kind of terms is corresponds to terms in which this energy difference is equal to 0. So then these terms are constant in time. And we have another kind of terms in which this energy difference is different from 0, meaning that it is oscillating. So if we define an effective equilibrium state as an infinite time average of this time evolving function, we have that only the first of these two contributions, the constant terms in this sum here, remains survive. So we have four different terms below the critical energy. We have this first one, which corresponds to the probability of the system having a positive parity. The second one, which is connected with the probability of the system having a negative parity. And the remaining two, which are connected with the coherence between these two parity sectors. As this constant C change the parity, these two guys here are linked to the expected value of this constant of motion. And this means that to get a description of equilibrium state, we need the information about the energy, which is important to select correctly the corresponding eigenstates, the parity values, which give the result of these first two terms, and the value of C, which give us the result for the second two terms. So what I'm going to do, I'm going to test these equilibrium states. I'm going to focus on the expected values of observables in this equilibrium state. And I'm going to work with a quench. I'm going to start with the ground state of the Dicke model for the coupling constant 1.5 times the critical one. And as this ground state is degenerate, I'm going to rely on the more generic combination of these two eigenstates. I mean, I'm going to make a linear combination including both the positive parity eigenstate and the negative parity eigenstate. This P corresponds to the probability of getting the positive parity or the negative parity, and I also introduce this phase here, which describes the coherence between these two parity sectors. Then I quench the system up to this value of the coupling constant. In this way, we are sure that we are still below the critical energy. We have tested this thing, and we calculate a long time average of physical observables. So it's important to know that the initial value of the parity is given by 2p minus 1, and the initial value of this constant of motion is given by this function here, which depends on both p and the phase phi. So I write here a negative sign because I am choosing the negative of these two solutions I presented you before. If I chose the phases in the relative phases of these two different eigenvalues in a different way, I can also get the positive branch. So in this case, I get this negative branch. So I'm going to test three different observables, and first of all, I am going to test if the initial value of the constant of motion remain the same during the whole time evolution. So here I show you the results for the Dicke model. We have done a large number of different simulations with different values of P at different values of this phase. The dot lines corresponds to the initial states described in the final equation of the previous slides, and the symbols are the values obtained after a long time evolution. This figure shows that the value C remains constant and is correctly described by the initial condition I have written before. So this is everything okay. C remains constant because we are below the critical energy for all this kind of initial condition. So after doing this first test, I proceed with different observables. First, I take a look of the number of photons, which is the order parameter for the standard quantum phase transition. And what I observe is quite boring. I mean, as all the initial conditions have the same energy, what I get is that all the time evolution gives rise to the same value for the number of bosons. And this is what we expect in standard thermodynamics. The final number of bosons, the equilibrium number of bosons, just depends on the energy. So this is a quite boring result. But this is not the only one I have. Here I show you the final result for the parity breaking observable, the first component of the angular momentum. So what I observe here is that this equilibrium value does depend on the value of this constant C. We can have either large value of this first component of the angular momentum, either very small value, negative values, or either zero, depending on the value of this constant of motion C. What we also observe is that the parity does not seem to play a relevant role because we get the same value for different values of the parity. This figure is interesting because it explains the result that Ricardo Puebla and I obtained a few years ago regarding this process here. Remember that we started in the Lipkin model with an initial condition having a large value for this parity breaking observable. This means that we were here on the left on this figure. Then we changed the coupling constant of the Hamiltonian up to we reach the normal phase in which this constant of motion is no longer this C operator is no longer a constant of motion. This means that in this phase here, this C operator start to fluctuate around 0. And when we come back, this operator got frozen at the value it had just previously to crossing this critical line, which was very close to 0. So when we came back to the original part of the spectrum, we were in this region here having a value of C very close to 0, and the consequences is that this symmetry breaking observable stayed close to 0, as we observed in this figure here. So I think that it is also a promising result because it explains previous results which were not so clear in this way. Finally, I showed you the result for the entanglement entropy between the atoms and the following, that this entanglement entropy also depends on the value of C. So, and again, we also observe that this entanglement entropy does not depend on the parity. So what we can conclude from all these results is that the value of this constant of motion is mandatory to describe what happens in thermodynamical equilibrium, because the first component of the angular momentum and also the entangled entropy do depend on this value. So with these results, we can get this phase diagram for both the Rabi and the Dicke model. Above the critical line, above the critical energy, we have a normal phase in which equilibrium states only depend on the energy and the parity. And we have seen that the parity does not play a very relevant role. Below the critical energy, we have an equilibrium state which depends on the energy, the parity, and this operator C. So we have completely different thermodynamics at both sides of the transition. As soon as I cross the critical line, I lose this constant of motion, and the equilibrium thermodynamics completely change. In particular, we can see that above the critical energy, this equilibrium ensemble is composed by wave function that have both well-defined values for the energy and the parity. I mean, I can understand this equilibrium density matrix as a set of wave function, all of them having a well-defined value for the parity. Below the critical energy, this is no longer true, because as the parity does not commute with this operator C, we cannot define a set of wave function having both well-defined values for the parity and this constant of motion. This means that in this phase, at least one of these two discrete symmetries has to be broken. So this is the reason why I call it symmetry broken phase. And with this phase diagram, I almost end my presentation. Just to summarize, the main finding of this work is this constant of motion, which is necessary to describe the physics, the equilibrium physics below the critical energy, and which is no longer necessary to describe the physics above this critical energy. You can read more about this result in this preprint, which is in the archive. And finally, just 2 words about future work that Angel is doing as his PhD thesis. He's working also on building statistical ensembles to account for the role played by C. So we know now that the equilibrium thermodynamics requires the knowledge of C, and we need a statistical ensemble that includes this information. And also we are interested in which consequences have the fact that we have two non-commuting discrete symmetries in this case. Of course, we are also open to study the same results in other in other system and to test if we can extend these results in more complex, even having 3 or 4 degrees of freedom. So I think this is all. Thank you very much for your attention, and I'm open to any question you want to do.
Okay, thank you, Armando. Thank you for your nice presentation, and you stick very well to the time. I can see hands, but these are hands clapping. So I now want to see hands, raised hands for questions. So anybody who has a question, or Alessio first, the first I see, Alessio Celli.
Sí.
Sorry.
Okay. So first of all, thanks a lot for the very nice talk. So I wonder whether all this could be displayed in terms of angular momentum, because somehow this parity and the C seems like that are Pauli matrices, right? So if I take 2 orthogonal parity matrices, they do the job. So I wonder whether one could think that a spin S, that is what is involved in this model, could be obtained as the tensor product of a spin S minus 1/2 times 1/2. And then we would have to subtract also the spin minus 1. But could be that dynamically, there are the phase in which the spin minus 1 has 0 energy or disappear from the spectrum. Somehow the spin S become equal to the spin S minus 1 tensor 1/2, and this explains why essentially one has the parity, these two Pauli matrices, let's say. So I wonder if you thought about in this direction. Obviously it's something that came to my mind now during the talk, so I couldn't try to check if this makes sense, but
yes, we have. Well, I speak about we because I'm including Angel, which is also working in this project. Yes, we have a test that this C constant and the parity have the structure like Pauli matrices, but we are not sure if they can be linked directly to the spin, say this SU2 algebra for the angular momentum. So we don't know if this structure like Pauli matrices is directly linked to the angular momentum or not. Do you hear me? Yeah. Do you hear me or not? I don't know. Okay.
Slow.
Hi.
A bit
or not?
Please. A bit
slow.
Okay. A bit slow, Armando.
Okay.
But I turn off your camera just in case. So try now. I think well, I could get your answer, but try now.
Okay,
I turn off your camera.
I can repeat it. O sea, the idea is that we know there is a SU2. Okay, the idea is we have a SU2-like structure involving this parity and this C operator, but we don't know if it's linked somehow to the SU2 algebra of the angular momentum, because I don't know how to link these two things. I think that this is a different SU2 algebra. We have to explore it. So this is a very good idea to explore it in detail. So I think that Angel is working in this idea. So maybe in a few weeks or months, I can give you a more detailed answer to this point.
Okay. Next question. Thank you, Alessio. Now, next question is Ami's question.
Okay. First of all, thank you very much. That was very interesting. I want to ask you two questions. One, you are showing us an example of a sort of energy-dependent constant of motion. sort of a constant of motion that is actually a constant only at a certain energy regime.
Yeah.
And my question is, I mean, can you show that, or how to show that it actually commutes with the Hamiltonian in that regime, or at least if you can you go to the classical limit of it and see that you get a Poisson bracket equal to 0 at energy less than the critical?
Okay, I think that it's probably complicated to get a proof. And the classical limit, I mean, I have a very strange operator because basically it's the sign of this q coordinate, meaning that if I am here, for example, in this trajectory, of course, the sign is always -1. And if I am in this other trajectory, of course, the sign is always +1. But as I have said, this dynamical function involving the sign is a bit funny for me because it's non-analytical. So I don't know if it's easy to calculate the Poisson bracket because I cannot derive it in terms of the coordinate and the momentum. Regarding the quantum case, besides any analytical calculation, which I don't know how to do it, probably the most compelling numerical evidence is this one here, as this sandwich involving the positive parity eigenstate, this operator, and the negative parity eigenstate must be equal to 1 if this operator C commutes with the projector, meaning that this operation remains in the same energy subspace. So this result shows that as I increase the system size, this is better fulfilled. I mean, if the system size is, let's say, 200 or 250, we get that this is equal to 1 up to the numerical precision of the machine. So, and this is not working anymore if I am above the critical energy. So maybe I can try to calculate the Poisson bracket, but I am not so much confident on this because this funny definition involving the sign, which is it's a bit ugly from my point of view.
Thank you very much, Armando. Now the next hand is Jorge Hirsch, and then Juan Diego Urbina. So first, Jorge.
Thanks, thanks Armando for this very interesting talk. And I wonder that, at least in my experience with the Dicke model, when you are in the low energy region and you go up, then the degeneracy between the different parity states is growing and growing. Obviously, when you arrive to the excited state quantum phase transition, there is a sudden change in the density of states, which is, as you mentioned, one of the characteristics. But I wonder if it is for the separation and even perhaps for your observable, it is a smooth change. So it is not a sudden change, but when you go up in energy, because you study here usually 3 different levels, but what happens if you study the same parameter for many different energy going up? Because it seems to me that it will a smooth transition.
Well, the problem is to reach the thermodynamic limit. So let's. I conjecture that this is an abrupt change, but this is a conjecture. I mean, from this figure here, let's see, this one with just 3 different energies. What I observe is that below the critical energy, the distance between two energy levels with different parity becomes smaller and smaller and smaller as I increase the number of atoms. So this made me conjecture that in the thermodynamic limit, this is 0, and this one is not 0. And the same happens for energy levels in between. But of course, I cannot be sure. Maybe you are right, and we are dealing with a smooth transition. I don't know. Maybe, I don't know how to explore this numerically, because even using your efficient basis for calculating the Dicke model, we are still very far from the thermodynamic limit. In the Rabi model, it seems more abrupt, because we can get to, let's say, a large number of particles understood like Ricardo explained the other way. But of course, if I am very close to this energy, this critical energy, again, I see a non-abrupt, a smooth change. So it's very difficult to provide a precise answer, and very interesting in any case.
Okay. Now Juan Diego Urbina is next.
Okay, thank you very much for the nice talk. Yeah, maybe I got it really wrong. So be my guess if what I'm saying is completely stupid. But can it be that somehow what you are doing is constructing an operator that accounts for the spontaneous symmetry breaking that one expects, for example, in the double well? I have a double well, finite double well, like the quartic potential, this thing like that. I have two minima on the one on the left, one on the right, and I know that when h bar goes to 0, the very non-perturbative corrections due to tunneling go exponentially fast to 0, and then eventually in the thermodynamic limit, I know that I will be localized on one side or the other. And of course, if I ask the question, if I construct an operator that asks in which side you are, it will be a constant of motion when h bar goes to 0. I mean, this is the standard scenario that we all know and love of spontaneous symmetry breaking. Do you think there is a connection with what you are doing here?
Yes, I think that this is basically the idea, to find this operator which labels in which side of the double well potential we are. Yeah. Yes, you got it perfectly.
Okay, in that sense, then this is expected to be quite generic scenario, right?
I guess so. Yes.
Okay. Thank you very much.
Are there more questions or comments for our speaker? Because I have a couple of them, but I'm the convener, so there is no one else has any question. So very nice presentation, a very nice work, Armando. This quest of some way of labeling states or some kind of an order parameter for the ESQPT. Will you call this, by the way, an order parameter for the ESQPT?
Not exactly, because it's not a thing which is 0 or different from 0, and depending on which side of the critical energy you are. Let's say that it is a way to define an explanation about which kind of order parameter we can find in this transition. Okay. Just let's say a dynamical difference which translates into thermodynamics. This is the idea.
And then regarding the two systems that you have used, that I understand, I think I understood why you have chosen Dicke and Rabi, because they are very well. There is a strong relation between the two, and one has 1 degree of freedom and the other has 2 degrees of freedom, 2 effective degrees of freedom. But in both cases, they are coupled to this bath and this radiation bath, and your operator depends on the bath. So I was just guessing when I was listening to you for example, if you go to a simple 1D model like the Lipkin, what will be, is there also a very direct and simple operator like the one you have chosen, this A plus A dagger in the Lipkin case?
I guess so, because I'm going to show your results that I think that they are obtained with the Lipkin model, no?
I'm not sure if this is the couple top, but because this paper there were the couple top and the Lipkin.
Yeah.
And I'm not sure now which one of the two, but probably it's the Lipkin. But well, they were very similar. So in any case,
okay.
it can be.
So in this case, probably the operator Q, it's also working because as you can see here in this critical value of the energy, the wave function crosses itself at Q equal to 0. That probably the same operator Q written in the terms that is written for the Lipkin model works. I don't know, but I mean, it's we intend that it is generic, and probably the most difficult thing is to find this operator. But in this case, I think that it's quite easy, and in fact, I can try to find it because I have all the codes to diagonalize the Lipkin model and to work with it. And probably it's just Q in this case.
Yeah, well, I'm not sure how easy it is to find a Q. Like it's not. I don't know if it's trivial to define this Q in the Lipkin. Because that's well, we've been struggling, and I got in contact also with Jorge and Saul Pilatowski about the definition of Q. How do you find Q? And it's not as easy as this A plus A dagger, but yeah. It may be. But then I was then because if this is general, that should be also applied to systems that go beyond 1D. Because Lipkin is like Dicke, but it is 1D. And then if you go to 2D, for example, the Vibron model or the IBM, or then thinking of the simplest case of the ESQPT, for example, U3 to SO4 in the Vibron model, or U5 to SO6. In this case, you really don't have two different minima. So you have a minimum in the origin that transforms into a maximum, and then you have this is something closer to a Mexican hat potential, let's say. Yeah. So though in those cases you also have this feature that you have degeneration, different degeneration above and below the separatrix of the ESQPT. This picture, it seems to be very much linked to a 1D case. And I'm not sure in a 2D case, how will this work? If you can extend this to 2D or 3D systems. Have you thought about this?
Okay, well, the Dicke model is 2D system because it has 2 degrees of freedom.
Yeah, but I was sorry, but I was. It has 2 degrees of freedom, but in some ways, like a couple Lipkin. Couple Lipkin has to. But each Lipkin is a 1D. But I was thinking it's simpler than a Dicke, much simpler, which is the Vibron model, which is just 3 degrees of freedom of the U3 Vibron model, which has 2 degrees. Is it two-dimensional? It's 1 degree of freedom, but two-dimensional. So that was my point.
Okay, I don't know, because the idea depends on the fact that we can find a dynamical function which splits the phase space. So I think that this formalism can explain excited state quantum phase transition, which fulfills this condition. If you have a thing like a Mexican hat, I don't know if it's going to work, but maybe I can take a look on the details of the Vibron model and think about it. Maybe we can find a solution for this case, I don't know.
I think this is going to be, because in fact this is still in a 1D case. If you have 3 minima, imagine a case where you have a more complex with 3 minima. In this case your formalist can be extended. I don't know if it will be designed directly. You have to define something different, but you can define something that tells you in which of the 3 minima your system is.
Yeah, in fact, Angel is now working with Hamiltonian having 3 minima. So we don't know still how to generalize, but it cannot be a thing because we have, let's say, 3 different angles labeling the 3 different parts of the phase space. At this moment, he's just struggling with the Hamiltonian, trying to understand what the Hamiltonian does, which is not so easy. And maybe if we success in this first part, maybe we are going to try to generalize this idea to a 3 minima to a potential with 3 minima.
Okay, so if this is the last opportunity, if somebody has a question or a remark or a comment for our speaker. If not, let us thank him again, because he has given a very nice seminar. Okay. And thank you to everybody for attending the seminar, to the audience. And next week, we will have another one. Juan Diego Urbina will speak about information scrambling. Okay, thank you very much for coming.
Thank you. Goodbye.
Thank you.
Bye.
Bye.
Thank you, Rulo,
Bye-bye.
Dani, Pepe. Thank you.
Bye-bye.
Bye, Jose.